So let's go over chapter 5. Now, I started with just a review of the functions of bone. So remember, of course, we have support, and supporting the body would be obviously a framework, but also this is also the attachment for your ligaments and your tendons, right? So ligaments, bone to bone, tendons, muscle to bone. Protection, and the most obvious examples, of course, would be the skull, ribs, and pelvis. The bone also helps movement because it provides resistance to the muscles. And the other things that you might not think of right away would be the formation of blood, and that takes place in the red bone marrow. So we have stem cells for blood in the red bone marrow. Mineral storage, of course, calcium, but also phosphate, and fat storage. So there's a lot of fat in the yellow marrow, all right? And I had mentioned this is why carnivorous animals will chew on the bones, because there's a lot of calories and a lot of, therefore, energy that is stored up in the fat of the yellow marrow, okay? And then bones are largely classified by their shape. So we talk most about the long bone, but we also have flat bones like the sternum, irregularly shaped bones. Obviously the pelvis would be in there, but here use the example of the vertebrae. Sesamoid bones, they're shaped like sesame seeds, and everybody has that in the patella. But of course, there could be a few more in the hands and the feet, depending on what you do with your hands and your feet. If there's a lot of repetitive movements and that sort of thing, you will get extra sesamoid bones. And short bones, so that would be like you would have in your wrist and in some of your ankle bones, but mostly in your wrist would be a lot of short bones there. Then we went over the structure of the long bone, and I actually spent quite a bit of time on this, drawing it out. But to review, when you look at the long bone, the long part, the shaft part, that is called the diaphysis. And the ends are called the epiphysis, all right? If you do the Google on this, you'll see that sometimes they will talk about a metaphysis, which is in between these two, but we don't really talk about that. In this course, it's a little bit hard to imagine where that is, so it's a little bit harder to think of that. But if you see it, it just means it's in between the diaphysis and the epiphysis. That's why it is meta. All right, so the two epiphyses are on the ends and the diaphysis is the shaft. Now, within the length of the bone, in the long bone, or in the center, you will find the yellow bone marrow where we have fat. And on the ends and the epiphyses, you will find the red bone marrow where we make blood cells. The other thing that you have around the outside of the bone is connective tissue called the periosteum. You will also sometimes see this outside of cartilage, all right? But depending on who you read, sometimes they will call it the perichondrium if it's outside cartilage, all right? So be careful there. But if it says periosteum, you can pretty much know that in this course we are talking about that connective tissue covering around bone. Then the next thing to remember is that the outer part of the bone is compact, and the inner part is what we call spongy bone. Okay, so spongy bone is arranged in these sort of lattice-like spongy looking appearance. That's why it's called spongy bone. And here it allows for the bone to be lighter, all right, because compact bone is much heavier, so this will loosen up the weight of the bone, or lighten up the weight of the bone. So I had mentioned that birds would have a lot more spongy bone. All right, but the outer part is always the compact. Now, the compact bone, and these exist in the spongy bone too, but the structure is a little bit different. You're going to have lacunae and osteocytes in the spongy bone as well, but we focus on the osteon, which is the arrangement of these structures in the compact bone, which are these cylindrical structures. And I will go over this again, but the middle part is the central canal. The structure itself is called the osteon, and the osteocytes are located in these little spaces called the lacunae, all right? Now, to get into this, I went over the different types of cells that we have in bone. So bone, these cells are actually from an osteogenic cell, or sometimes it's called the osteoprogenitor cell. This is a stem cell that differentiates into bone-forming osteoblasts, okay? So the osteoblasts are the ones that will form bone, and they will, what will happen is that they'll get trapped in the bone, and they will then become mature bone-maintaining cells called osteocytes, all right? Now, the other cells that we have are these cells called osteoclasts, and the osteoclast, it comes from originally a bone marrow bone marrow, I should clarify that, but a stem cell for making blood, okay? But it is a multinucleated cell. It does not come from the osteogenic cell here. It comes through a different lineage, and that lineage would be through the blood-forming cells that are found in the marrow. In the red marrow. So these osteoclasts are specialized cells. They're sort of like macrophage, but we call them osteoclasts because their job is to break down or resorb bone. So remember, the osteoblasts and the osteoclasts work in harmony with each other to maintain bone. All right, now let's go over the osteon. So here down the middle is your central canal. This is where we have our blood vessels and our nerves. And then we have these concentric layers of bone. And remember, this is like tree rings. So it's not just one little disc. It's like a whole column of bone. And each of these rings are called lamellae. And within those lamellae, you'll see these little spaces called lacunae. And it is within these little lacunae that the osteocytes live or exist and maintain the bone and respond to pressures. And remember that I had gone through this whole idea about the fact that the blood supply is here and these cells are way out here, so how are they going to get their nutrients from the blood? Now, as we saw back here, there is a good network of blood vessels in the bone, all right, because blood is well vascularized, but these cells are still trapped within this hard matrix. So what these guys need to do is get their nutrients, and they do so using extensions or cellular extensions that exist between the cells that extend through these little canals or canaliculi within the bone matrix. So here these are like little canals inside the bone, inside that hard matrix, and the cells extend parts of their cytoplasm and their cell membranes in there, and they touch the next osteocyte. And when they touch there, they form a gap junction. Remember, the gap junctions are the ones that allow for the cytoplasm to be exchanged between the cells. So in this way, cells that are closer to the blood can pass nutrients to these cells that are further away. And then the waste can go from cell to cell to cell to cell back to the blood vessels. So they sort of have like a bucket brigade idea where they can pass things. And here you can see with these little red extensions. So the osteocytes and the lacunae, then we have the canaliculi and the central canals in there extending out through here so that they can get what they need. Now remember, bone is a structure that's constantly reforming, all right? It isn't static, so I had said to you that the figure that I've heard is about 7 years for you to completely turn over your skeleton, all right? Now, this one is just another look at these cellular extensions between these osteocytes through the canaliculi. And here, this artist's rendition, you can sort of imagine these cells are extending and touching each other in 3 dimensions. Because I know when we show these pictures, it gives it sort of a 2-dimensional view, but it really is a 3-dimensional structure, okay? Here you can see the cell membrane and the extensions of the cell membrane. The cytoplasm through there is the nucleus, nucleolus, okay? And that's how the system works. Now, I mentioned that dense connective tissue, the ligaments, those are the ones that are connecting bone to bone, and here you can see several of them here in this knee joint, all right? These are closely packed collagen fibers, Remember, the cells that produce these connective tissue fibers are called fibroblasts, right? So ligaments, bone to bone. Tendons we'll talk about in chapter 6. Those are the ones that join muscle to bone, all right? Make sure I'm not forgetting anything important here. Just going without looking at my notes. All right, then we have the cartilages of the body. All right, so we have three main ones. We have the hyaline cartilage, which again, I will say right now is your articular cartilage, the one that is formed on the ends of the bone, right, where you have an articulation or a joint. We have other examples of hyaline cartilage in the body. You'll see that in the trachea. But I had mentioned in class, and I'll do it now just in case I forget, that the hyaline cartilage that you get that you're born with and that you develop before maturity is the hyaline cartilage you're going to have. So later on, if you damage your cartilage, it gets replaced by this one, the fibrocartilage. And you can see there's a difference here. So the hyaline cartilage, the matrix is flexible like any cartilage, or sponge, no, not compressible, I should say, not spongy, compressible, which is why it's found in the ends of the bones where we have joints. But here, the collagen here is very thin bundles, so you don't actually see it. It sort of gives it sort of this glassy appearance. And remember, again, with cartilage, we have lacunae, and the cells here are called chondrocytes. Don't forget that, all right? Now, the difference here between hyaline and fibrocartilage is you can see this. The collagen bundles are much thicker here, all right? So this is a very strong cartilage. It's not the best one to have in a joint because it's not smooth and glassy like this. This is why if, as an adult, you damage this articular cartilage and you get this fibrocartilage, almost like scar tissue to seal it up. The joint is never quite the same again. So if you're someone who has had this problem, you'll be able to vouch for that. But we do have other uses for fibrocartilage, and that this fibrocartilage will be found where we have highly compressible situations. So like your intervertebral discs are made of this. It's the cartilage at the pubis as well. And as you'll see, we have this inside joints, pads of this called menisci, right? Then we also have elastic cartilage, which looks very much like the other two, but the only difference is that we've got elastin fibers as well, okay, which are elastic, okay? The protein here is called elastin, and it gives that flexibility. So like you see it, you find it, you don't see it. You find it at the end of your nose and around the shape of your ear, okay? Your pinna has that elastic cartilage in there. So it bounces back, and that's what elastic means. Okay, so now the thing I wanted to stress about this hyaline cartilage at the articulations is that it really is continuous with bone. All right, it's not something that you can peel off, and this comes back to bone formation later on. I'll go over that again. But here we have cartilage, and it becomes calcified, and gradually there's this sort of transitional layer that becomes bone. So here we have our nice hyaline cartilage. You can see that glassy look, and then it becomes calcified. And eventually we have osteocytes and bone, right? So it is a continuous structure, and that's something that I want you to keep in mind. All right, so articular cartilage is found where the bone forms a joint surface, so where bone moves against another bone. Right, so here you can look at the joints. I'm going to talk a little bit about joints. So here you can see, I really like, this is from a cadaver, so this is real what it looks like, okay? So here you can see the compact bone on the outside, the spongy bone in here, so this is where you're going to have, this is the epiphysis, this is the femur, the epiphysis of the femur. And you can see that this would be where the red marrow is, and the yellow marrow would be in here, okay? And you can see this nice, smooth, articular surface, which would be covered with your hyaline cartilage or your articular cartilage, all right? The same thing here, even though this is an irregularly shaped bone, you can see the outside is compact, the inside is spongy. All right, so we have a classification of our joints. We have the immovable joints, which are called fibrous, okay, but there is, and this is like the classic example between the bones of your skull. Fibrocartilage at the pubis, all right, and also here between the vertebrae. So this is a little bit, has some motion allowing for some motion, and this is called the cartilaginous joint. And of course, your fluid-filled joints are the ones that allow the most motion. These are your synovial joints. And here we've actually got a capsule. Here we have that secretory epithelium. One of our classifications, I told you it was a synovial membrane, produces synovial fluid, and it fills this area up with liquid. And this is the most movable joint, okay, your synovial joints. And I wanted to stress that those fibrous joints of the skull start off as fontanels, all right? So as you know, the head of the infant is very soft. And this is because these sutures here, all right, are not fibrous yet. They're called fontanels, and this allows for the skull to compress. So this is so that it allows still protection, but allows room for the brain to expand until maturity. So actually, if you are not quite 18, your fontanels are still not quite solid. So I pretty much guarantee you when you're 20, they should be done. But as your brain is developing, okay, and I know as teenagers you might not want to think about that your brain is still developing, but it is, and it's still not quite solid yet, okay? The other thing here is, of course, the head has to be a little flexible to allow for delivery, right? Because the head has to squeeze through the cervix. All right. Okay, so these synovial joints, I had mentioned, there's the synovial membrane mixes synovial fluid. Okay, now we also have other structures. So this is where we have the ligaments that actually come through, all right? So some ligaments stay on the outside of the joint, but there are some ligaments that actually become part of the joint, go through the fluid-filled capsule like the ACL, all right? So another reason that this ACL is always so difficult to heal. Now, the other thing we have are those fibrocartilage discs that sit inside the joint, which are called menisci. All right, so here in the knee joint, there's a medial one towards the middle and a lateral one towards the outside. These are fibrocartilage, all right, and they just sit in there, extra padding. It allows for a little extra protection of the bone. Now, we also have bursae, or bursae, and these are fluid-filled sacs, cartilage, all right? This sort of like a cartilage kind of connective tissue. It's a little hard, but the middle is fluid, and that's synovial fluid that's sitting inside these little sacs, and that acts as a little extra padding. And here you can see there's 3 around the shoulder joint, all right? Yeah. Now, types of synovial joints, I just mentioned 2 of them in this class. First is the hinge joint. So the hinge joint is where a convex surface fits into a concave surface. And then we have this opening and closing action like a hinge. And the elbow is an example of that. Okay, so one to think about here. Then we have the ball and socket joint, where we have literally a ball that sits into a groove, right? Like a cup-like surface. And this would be here, the hip joint. And this allows the most movement of any joint. Now here we also have, as I mentioned, the hip and shoulder joints are examples of that, okay? Then we have joint movements. Okay, so some of these movements, and there's a lot of movements that occur at the joint, but we just mentioned some of them in this course. So if you take A&P, you're going to learn a whole lot of special movements. Here we just have flexion and extension, just as you can see in the picture here. So this would be like your hinge joint. Coming and closing would be flexing, and opening would be extension. The shoulder joint has a little bit more freedom of movement, right? That's a ball and socket joint. So it can flex and it can extend, but it can also hyperextend. So it goes a little bit further than what you would be thinking of, all right? Let me just go through and get ahead of my slides and my notes here. Okay, then we have the abduction, okay, which is pulling you away from midline, and adduction is toward midline, all right, and this would be the shoulder joint. midline being this line down here of the body. I know if it looks like you're going back to the middle here, but actually you're going, if you think about the way the joint moves, okay, you're opening the joint, so you're abducting here, okay? Circumduction is when you can make sort of like a cone with the body, so part of it is going around, you're making a circuit. I think your course textbook has another example of what this looks like, and they use the shoulder joint, I believe. Then we have rotation. So the obvious one would be shaking your head no, right? But we also have medial and lateral rotations with the rest of the body, but you can see that it's pivoting because here we have these ball and socket joints. They allow the most freedom of movement, so you can also have rotations around these ball and socket joints, okay? So that occurs here as well. Here we have the atlas and the axis, which allows that pivoting rotation around of the head, okay? Okay, then bone development. So I spent quite a bit of time on this, but I really want you to be able to put these steps together and have it make sense, all right? I'm just going to talk you through it again. When in class, I wrote all the notes and I drew pictures, but, or I didn't write, I drew pictures. But so at the beginning, we have this idea where we have a cartilage form. And this is called ossification of a long bone because we're starting with a cartilage form. There is another type of bone formation that we don't talk about in this class, and that's where osteoblasts literally make bone on their own without a form, okay? But we talk about in this one the ossification of a long bone with starting with a cartilage model, okay? So here we have the chondroblasts. They've made this hyaline cartilage form, and this is in the fetus, all right? And what will happen there is that the chondrocytes and the chondroblasts that are there start to die off because you can see they're not getting a good supply of nutrition. And as they die off, the cartilage actually starts to break down. And this sets up a trigger, and it actually causes the formation of the periosteum. And it also causes blood vessels to come into the structure. So this is angiogenesis, the formation of blood vessels. But these blood vessels will now come in, and when they do so, they bring with them the osteoblasts, okay? Now these osteoblasts, they will secrete a matrix, okay? It's basically a scaffold. And this scaffold is called osteoid. And it's largely made out of collagen. And this osteoid is really good to allow crystals of calcium and phosphate, which is called hydroxyapatite. Right here, I can see the name is here. These crystals of hydroxyapatite will stick to the osteoid form and basically now harden this matrix. And remember, when we have the osteoblasts, they become trapped in that matrix and they become then osteocytes, all right? Then once the bone is hard, so think of birth, then from birth onward, okay, we still have a bit of cartilage there where we still allow for this formation of bone from a cartilage model, and that is in the growth plates, all right, which are also called the epiphyseal plates because they're at the epiphyses of the long bone. And these allow for the bone to grow in length. Now, it doesn't cause the width, okay, so the bone lengthens and widens, but it widens a little bit on the end, but here on this part also has to widen, which is where we also have this idea of appositional growth. And that isn't done starting with a cartilage model. It really literally has to do with the cooperation of osteoblasts and osteoclasts along the diaphysis of this bone, all right? So, I mean, obviously this cartilage is going to get wider as the bone gets thicker, all right? But this appositional growth is what gets this part wider, all right? And the growth plates allow for the bone to get longer, okay? All right, so appositional growth for the thickness is not caused by, does not start with the cartilage model as the length does. Okay, so the length has that cartilage model at the growth plate or the epiphyseal plates. Okay, so if you looked here on this side, so it's lengthening on the diaphysis side, you're going to have chondrocytes in here laying down new cartilage, and that will gradually become ossified as the osteoblasts get in here and harden that up. Okay, and then remember, appositional growth with thickness along the shaft or the diaphysis of the bone is caused by the cooperation of the osteoblasts and the osteoclasts, all right? So here you'll see, again, remember that continuation of cartilage to bone, all right? So this is going to be on this side, so this part is going to be bony, this side is going to be cartilage. So here we have our cartilage, and it gradually becomes, and you can actually see there's more blood vessels here as well, and you're going to have blood cell formation in the red marrow. So whereas here, where we have the hyaline cartilage, it's poorly vascularized, but we have the chondrocytes here, and the osteoblasts and osteocytes here, and then we have blood cell formation. So the two growth plates, remember that it's lengthening from both sides, all right? So there's both growth plates on each side. And I had mentioned to you that by x-ray, it looks like this is like a big space here, but really this is filled up with cartilage, okay? This is a continuous thing. And the thing is, on an x-ray, it's the bone that lights up brightest. So it gives the impression that there's actually a hole here or a space here. And it really is, this is where the cartilage is. And remember that cartilage and bone are continuous with each other, all right? So then we watched a little video on bone remodeling. And I wanted to stress again that the bone is constantly doing its thing. It's breaking down and building and breaking down and building. And there's this sort of continuation between the osteoclasts breaking down. They give off growth factors. It causes the osteoprogenitor cells to proliferate. And the osteoblasts, as their progeny, end up building bone. And, you know, these osteoblasts and osteoclasts work together for remodeling. And we have this for many different reasons, right? Because we use calcium all the time, so we have to replenish it. But also as we develop, we've got stresses on the bones, and we're constantly remodeling our bone. Let me catch up with my notes again here. All right, so whoops. The thing I wanted to stress here in terms of remodeling as an example is that as the bone develops, and just so you start taking up a type of exercise and you're changing the stresses on the bone will, not overnight, but it will over time, will remodel itself to equalize the pressures across the bone because the bone doesn't want to break, right? So it's going to do its thing, and it will change its shape to modify itself towards the type of activity that you are engaged in. So you can see that not only does the skeleton remodel, but it can also change its shape to adapt to changing conditions, right? Okay, then healing of bone. All right, so here, what's happening, and there's these 4 stages, and I kind of like you to know these stages. And it goes part and parcel with bone formation from a cartilage model. So if the bone breaks, what will happen first is that fibroblasts are going to make a blood clot along with the platelets and everything else. We'll talk about blood clotting later. But the fibroblasts here are going to lay down this sort of matrix of proteins. And within the blood clot, and this is called the hematoma, right? The blood clot is a hematoma. And we've got fibroblasts making sort of scaffolding of different types of tissues, different types of proteins that are connective tissues. And that then, also within there, we'll have macrophage that are cleaning up all the dead bone that has broken. Now with this, a blood supply will really form nicely into this sort of scar or this hematoma, and eventually one will get a callus. And this callus, at first, is made up of cartilage, specifically fibrocartilage. And so then we have chondroblasts in here that are laying down this cartilage, and it's being maintained by the chondrocytes. And then with time, the osteoblasts will come in and convert this cartilage callus into a bony callus. And it will first be spongy bone, and then the cooperation of the osteoblasts and the osteoclasts, we will then get a nice reformation of compact bone. So we'll have bone remodeling that takes place. All right, so that cartilage callus, bony callus, and then it gets replaced with compact bone. All right, so that's the stages and the healing of bone. Now this I really want you to know, and there will be, without a doubt, questions on this. So get this whole system straight, please. I know I sound desperate, but I'm not quite sure how, how to have you understand this other than you guys really have to think about it. So remember, bone is a place where we store calcium, and calcium is so important in the body, all right? And the easiest way for the body to get calcium is from the bone, right? So we have a negative feedback system here. And remember, negative feedback system is when it oscillates around a set point. So we have a certain amount of calcium that we need in the body. And it's listed here. You don't need to remember this number, but just know that there is a certain amount. It ranges between 9 to 11 milligrams of calcium per 100 mils of blood, okay? And you have about 5 liters of blood, right? So, and there's sensors in the body, not in the bone, but in the body that will sense the blood calcium levels, all right? Now, if blood calcium levels rise, okay, if they rise, what we want to do is store that extra calcium in the bone, all right? Now, remember, what are the cells that build bone? Those are the osteoblasts. Remember, it starts with a B, and they are builders, okay? And they are told, they don't know, they're not sensors, but they're given a cue from the body that blood calcium has risen. And that cue comes from the thyroid gland. So it releases a hormone, and that hormone is called calcitonin. Now, that's the other way to remember that calcitonin is the one here is because it has calcium in it. So when we have extra calcium in the blood, calcitonin is released from the thyroid gland. That then stimulates the deposition of calcium into the bone. And who's going to do that? The bone builders, those osteoblasts. All right. And then what's going to happen is, as a consequence, the blood calcium levels will go back down. All right. Now, what if they go down too far? All right. And then if they go down too far, the body is going to want calcium back in the blood. Where is it going to get it? Well, from the bone. I'll go over another 2 places it will get it, but the quickest way is from the bone. And this is the thing that really drives mostly through adulthood is this one. Calcitonin isn't as important in adulthood, but this one, this end here, parathyroid hormone, all right? That's the one that is released when the calcium levels go down. Parathyroid hormone is released from the parathyroid glands, okay, which happen to be attached to the thyroid gland, all right? These parathyroid glands release parathyroid hormone, and who are they going to stimulate? Well, the ones that break down bone. Those would be the osteoclasts. So parathyroid hormone is going to stimulate those osteoclasts that are going to break down bone and release calcium into the blood. So as a consequence, blood levels of calcium will rise. All right. So hopefully you have these two, this circuit together. All right. There's some players here, but I know you can do it. So just go over that. Now, parathyroid hormone also does 2 other things because there are 2 other ways that the body can get calcium. All right. So one of these is to reduce the calcium lost through the kidney into the urine. So parathyroid hormone will increase calcium uptake in the kidney. All right. So that's function 2. The other place we can get calcium is from our diet. As you know, this is why we need to get calcium in our diet, right? Our milk products. Now, parathyroid hormone is involved with this as well, although a little bit indirectly, Okay, so what it does is it helps to increase calcium uptake from our diet by stimulating the production of vitamin D. Vitamin D is what we need in the gut to help us bring in calcium from our food. Now, there's a little bit of a pathway here. We always think of vitamin D as the sunshine vitamin, but the final version of vitamin D is not produced in the skin. And the point here, I just want you to see that we make the first form of vitamin D in the skin, and that gets modified in the liver. Okay, and some of it we can get through our diet, but this has to be modified in the liver. And then the final form, this circulates through the blood. The final form actually gets produced by the kidney. And the kidney is stimulated to make that final form of vitamin D by parathyroid hormone, right? And that's going to help us maintain that calcium balance. This is why if someone has osteoporosis, they take calcium plus vitamin D, right? Because if they just ingest the calcium and they don't have enough vitamin D to help bring that calcium in from their gut, from those capsules that just ate, they won't be able to efficiently bring it in if they don't have enough vitamin D, right? So this is how that works. Okay, now this last part is really stuff you just got to sit down and learn, okay? You need to know the bone list, all right? The bone list is in the study guide, all right? I don't have it hard copy printed out in front of me, but the study guide has the bone list. And I'm just going to quickly go over these bones, but you gotta look at this and sort of learn where they are, all right? So the skeleton is made up of two parts, the axial skeleton and the appendicular skeleton. The axial skeleton being the axis, and the appendicular skeleton being the appendages. Okay, now I'm going to start with axial, all right? So here you see some of your bones that you need to know, your skull, frontal bone, right? At the back, we have the occipital, and on the sides, we have the temporal. This one at the top, there's two of them, parietal bones. The other one you should know is the mandible and the maxilla, right? Then, of course, we're going to have the sternum and the ribs, and we also have the vertebrae, okay? Now, if we go through this, here you can see these bones of the skull a little bit better, so you can sort of see you've got two parietal bones, you've got one frontal bone, one occipital bone, you've got two temporal bones. These facial bones, I don't believe you need to know for this course, but I would like you to know your maxilla and your mandible, okay, which holds your teeth and allows your mouth to open and close. All right. The other bone that we have is this floating bone called the hyoid bone. All right. It's not articulating with anything, but it does hold things and is a support for muscles, and obviously you can see their larynx here. We're going to talk about that when we do respiratory. Just looking at my notes to see what other things I wrote down here. Okay. Then here, of course, we have the sternum. There's three parts to the sternum. You don't need to know the three parts for this course, but there's the three parts here for the sternum. And then we also have the ribs, okay? Now we have 12 pairs of ribs. 2 of them are floating and 10 are attached. So attached ribs, these ones here, 1 to 10, these ones are attached to the vertebrae. And on the other side, through costal cartilages, all right, to the sternum. Now, then we have these 2 floating ribs down here, all right? These ones are attached to the vertebrae, but not to the sternum, all right? So those are the ones that are floating. So why do we have the rib cage? Well, it protects our lungs and heart, sternum especially for protecting the heart. Vertebrae, all right? Between each vertebrae, we have, as I mentioned before, that fibrocartilage disc. When someone has a herniated disc, what happens is that piece of that cartilage gets squished out and it pushes against the nerves, and that's why it's so painful, all right? So if you throw your back out, this is why it hurts so much, all right? I did that last summer. Fortunately, it healed up, but wow, that was painful. I was just out in the garden and just twisted myself in a weird way. And boy, even putting the kettle on was causing me pain. It was just ridiculous. So yeah, but it takes a while for this to heal up, and sometimes people need to have this surgically repaired. All right. Okay, now with these ribs, we have quite the arrangement, all right? So we have 7 of, what did I say, ribs? Of these vertebrae, we have quite the arrangement. We have 7 at the top, which are called cervical. Then we have 12 thoracic. Then we have another 5 lumbar. Then we have the sacrum, which is made of 5 fused ones, and the coccyx, which is made of 4 fused bones, all right? The easy way to remember this is that we have 7 cervical, 5 lumbar. Add those together, what do you get? 12, and that gives you your thoracic, all right? And then you just have to remember 5 fused sacrum and 4 fused for the coccyx, all right? And we have these curvatures are very standard in the human, okay? And then we have some odd little curvatures that can happen that cause problems. So one of them would be scoliosis, right? So this is where we've got side to side shifting of the curves, all right? So it's a sideways, often set back in line using a rod. I've had students in my classes in past, maybe one of you have a rod down your back to help straighten out scoliosis. But we also have 2 other curvatures, and these ones are forward and back. So kyphosis is where we have that sort of hunchback kind of situation. This is due to aging, osteoporosis, poor diet, vitamin D, not enough vitamin D, so we get a calcium deficiency, and it causes this to bend forward, so it's kyphosis. Then we have lordosis, which is this part, the reverse, where this part sticks out, okay? And this can happen as a result of pregnancy because of the weight of the baby, but it can also be to osteoporosis and weight gain as well. That's really all we want you to know about this. Then we have the appendicular skeleton. So these would be your appendages, all right? And that which holds them. So your clavicle and your scapula, as well as your pelvic girdle, all right? So we go through these. We have 2 clavicle and 2 scapula. We have our humerus, which is the upper arm. Then the forearm is made up of 2 bones, the ulna and the radius. So the radius radiates around the ulna. So that's the one, the ulna is the one that's not by your thumb. So the radius is by the thumb. Okay, so that will help you try to remember that. It's also, the radius is also the bigger one. And then in the wrist, we have 8 carpals. And then we have our fingers. So here you have 5. So we have 5 metacarpals. And then we have 14 phalanges. All right, so there's 3 for each of these digits. You're wondering, why is it not 15? Well, that's because the thumb only has 2. All right, it doesn't have the 3. All right, so this is why we lose the 1, all right, when we come to the phalanges. Now, when we come to the leg, all right, so we have our femur, patella. Then we have the tibia. The tibia is the big one, right? So think of it as a T, tibia, whereas the fibula is the smaller one. And you might be wondering, why isn't the forearm and the lower leg, why is not that just one bone? Well, think of how heavy that would be. So it's actually lighter. There's connective tissue here, a membrane that holds these 2 together. But if this was all solid bone, it would be incredibly heavy, right? Now, tarsals is what we have to make up the ankle. We have 7 of those. Then again, since we have 5 toes, we have 5 metatarsals. And again, we have 14 phalanges, again, because we lose 1 phalangeal bone at the big toe, all right? So instead of 15, all right? Okay, now in terms of the pelvis, there are differences between the male and the female pelvis, and I have them summarized on the slide. So the male pelvis is heavier and more narrow than the female, which is rounder and more flared. The opening here is smaller in the male than it is in the female. The pubic arch, this one here, is less than 90 degrees in the male, and it's a V shape, whereas in the female, it's more of a U shape and is greater than 90 degrees, right? Because that's because women give birth. So this whole area is bigger because the baby has to go through here. Okay, so those are the differences between the male and female pelvis. all right? Then we have a couple of ailments that I'm going through. So osteoporosis. Now, this largely gets worse as one ages, and that is because our stem cells slow down, and therefore our osteoclast activity outweighs our osteoblast activity. So we have to do other things to try and keep that bone building, and one of them is to do exercise, to stimulate bone formation through movement. Now, the osteoporosis, basically, like I said, you can see the difference between a normal matrix and an osteoporosis one. You can see this is a lot more spaces. This man has osteoporosis, got the kyphosis here, the hunchback. And that's just because his bones are becoming fragile and it's susceptible to breakage. So ways to work against that. Calcium and vitamin D, as I mentioned, this to increase blood calcium levels and slow down that osteoclast activity. They also will provide hormone treatments, all right? This is one of the reasons that these things slow down, because especially females, they lose their estrogen levels as they age, and that sort of slows down the building activity in the stem cells, all right? Then we also have sprains, right? So sprains are stretched or torn ligaments. And these actually heal very slowly because remember, ligaments have a poor blood supply, right? Then bursitis and tendonitis, so that would be inflammation of the tendons or the bursa, all right? So here I'm showing the foot because we have bursa back here, and I've had this bursitis in the heel. Oh my gosh, that hurt. But inflammation here, okay? Because here we have two more of those little sacs of synovial fluid sitting here, all right? So inflammation and irritation if there's a lot of friction going on here in use. Then we have the two types of arthritis, the main ones, all right? So rheumatoid arthritis, all right? This is the one that causes inflammation of the joints. It's all around the body. It's autoimmune. Okay, so what happens is that you raise antibodies to your own synovial membranes. It causes a lot of pain and swelling. It can happen at any age. I have friends that are 10 years younger than I am that have rheumatoid arthritis, and multiple joints are affected by this. Okay. Now, the other one is the osteoarthritis. This is one that happens more as one ages. Okay, and what happens in this case is that it's just wear and tear of the joints. It breaks down. You're going to replace that hyaline cartilage with fibrocartilage, makes it even more irritating. The joints affected can be isolated, right? Very often the hands, because the hands are used a lot, right? So you get this sort of cricking of fingers in the joints here. And this is progressive with age. I was trying to think, it's very painful, obviously, because of the inflammation. But this is not an autoimmune reaction, the osteoarthritis. Okay, so if you look at the difference here, so if you have a normal joint, what's happening with osteoarthritis is that these bones are starting to wear and tear. The cartilage, the hyaline cartilage is gone, the rubs together, it causes irritation. Whereas rheumatoid arthritis, we have swollen and inflamed membranes because the body is reacting or recognizing it has an immune reaction to the membranes here. And this produces a lot of acid, and that also causes the bone to break down, which is the other problem that one has here. But you can see that it's pretty much intact, all right? So very different reasons. Now, the third one is the gouty arthritis. Now, this is a different one. What happens here is that the joints become inflamed and swollen and irritated because there's buildup of uric acid crystals in the joint. And it usually happens where the circulation is a little less extensive, so in the extremities. So in the big toe is the big example, but here you can see this woman has it in her hands, okay? And it's very painful, and it causes this inflammation. You can see some of them are open sores here. But yeah, so this is what's going to happen with the gouty arthritis, okay? And uric acid, that is a byproduct of protein metabolism, all right? I don't know for certain, but I would guess that if there's a high protein diet, so a lot of meat, perhaps one could modify the diet and help this gouty arthritis. But you could imagine that it partially could be circulatory problems as well, because that uric acid is building up there, all right? Uric acid crystals. So there's so much uric acid that it's actually crystallizing out into the joints. And then I have this review video, and you know, it's really interesting. It's about, I think it's about 10 minutes, but it goes over everything that we talked about, and there's some other interesting stuff in there. So if you can watch it, please do. Okay, I think that is it. Yes. All right, so let me turn this off.